years and turn it into kilometers. And so the distance would become 110 times 10 to the 13th power kilometers, which if I wanted, I could convert to standard form. I could make it 1.10 times 10 to the 15th kilometers, but your calculator would be perfectly happy for you to put 110 times 10 to the 13th in it. And then the angle between them, there's a formula to plug into, and if memory serves, the angle, if we call this the theta here, the theta would be 206,265 arc seconds multiplied by the separation between them and the distance away from us that they are. So it's a matter of plugging into that formula, 206,265 arc seconds times 50 times 10 to the 6 kilometers divided by 110 times 10 to the 13th kilometers equals some number. I don't know, I'd have to put it in my calculator, in order to figure that out. But that's what you would do for it. So it's a matter of, the main thing here is knowing that you have to convert, that you have to put the separation between them and the distance from them both into the same units. That's the main thing to realize. Other than that, it's a matter of plugging into the formula. And if I then, this would be the number of arc seconds. If I wanted it in degrees, I would have to convert by knowing that there's 3,600 arc seconds in 1 degree, or 1 degree of 3,600 arc seconds. So in other words, whatever that number is, that would be question mark in arc seconds. I would multiply that by the fact that 1 degree is 3,600 arc seconds. So I would take that number and divide by 3,600, and that would be how many degrees the angle was.
Wait, so you took 100. How did you get the 206, 265?
It's the number of arc seconds in 1 radian. So it's just a number that I know is what it comes down to. And your book would have that formula in there. Yeah, so that's if we wanted in what's called radian angle, then it would just be the distance between the distance between them divided by the distance to them. That would give you the angle in what are called radians. And there happen to be 206,265 arc seconds in 1 radian, which is why we have to multiply that by 206,265 in order to convert it into arc seconds in that case.
So I plugged that in and I got 0.009.
Yeah, so it's a very tiny.
But that, okay.
Yeah. 0.0, like for arc seconds, you mean, after you did the.
I think that was in degrees.
Did you plug this in? Like
Yeah, I just did that top equation.
Right, yeah, that'll give you the answer in arc seconds.
Oh, I see.
Yeah, that'll give you the answer in arc seconds.
Oh, okay.
And then if it says you're looking at it with an angular resolution of some number,
You just convert it.
then, well, no, but so in other words, it could be like, okay, and then you're so I'm just going to assume you're right, that it's 0.009 arc seconds. And then let's say you're looking at it with a telescope whose angular resolution is 0.5 arc seconds, just making something up. If they're 0.009 arc seconds apart, and your angular resolution is 0.5 arc seconds, would you see them separately from one another through your telescope, or would they appear to be blended together?
You'd be able to see them, right?
So their angle between them is smaller than the angular resolution of your telescope.
Oh, so you wouldn't.
So you would not be able to see them separately. If their angular separation is smaller than the angular resolution of your telescope isn't good enough to tell them apart. They're too close together for your telescope to be able to tell them apart. So in that kind of comparison, the question is, are they closer together than your telescope can tell them apart? If their separation is smaller than the angular resolution of your telescope, you can't see them separately. If it's bigger than the angular resolution of your telescope, you are able to see them separately. That's why angular resolution is better when the number is smaller. The smaller the number of the angular, the smaller the resolution, the smaller the angular resolution number is, the closer things can be to one another and still have you be able to see them separately from one another. Small is good when it comes to angular resolution because small means you can see fine details, slight differences in position from one thing to another. Yes?
Could we expect to see an equation that talks about finding the diffraction limit between two things on the exam?
It just so happens I'm not going to give you a calculation problem involving the diffraction limit, but what you should understand is the idea that bigger is better in terms of the diameter and smaller is better in terms of the wavelength. That if the diameter is bigger, that makes the angular resolution better, i.e. smaller. If the wavelength is bigger, that makes the angular resolution worse, i.e. bigger. Because the formula is a number multiplied by the wavelength divided by the diameter. And since smaller is better and wavelength is up on top, increasing the wavelength makes things worse. Since smaller is better and diameter is down on the bottom, making the diameter bigger makes things better because it makes it smaller number of cells. So I do want you to understand that fact, that for the best angular resolution, you want a bigger diameter of the telescope, and you also would prefer to be working at a shorter wavelength, although you may not have the choice. If you're doing radio wave observations, you're dealing with radio waves, so that's not your choice in that case. Yes?
Should we expect a math equation dealing with like the total area covered by solar cells and like energy consumption?
In general, in tests like these, I tend to emphasize things where you don't necessarily need a calculator in order to do the comparison. So I'm more interested in testing you on things like, if I doubled something, what would happen? If I tripled something, what would happen? That sort of thing.
The fundamentals.
The fundamentals, and again, it's because in a lot of ways, you're exercising your brain more when you're not just putting numbers into a calculator, when you're understanding what a formula means. Putting numbers into a calculator doesn't necessarily tell you what a formula means, but understanding what will happen if I change things in the formula, that's really what's involved in understanding what the formula actually means.
I have a question regarding the quiz.
Yep.
In order to understand star clusters, we need to be able to estimate their ages.
Mm-hmm.
And what technique do scientists use? It said finding the main sequence turn-off point of the stars.
Yeah. Ask me that in the either after the exam or in the review session for the final exam, because I took star clusters off what you're required to know for this exam.
Oh, okay.
So we're going to be talking about that soon in class.
Okay, thank you.
Mm-hmm. Yes.
How does the strong force relate to the role that neutrons play in a nucleus?
So take a pair of protons. do they attract or repel due to their electrical charges?
Repel.
They repel. How about a pair of neutrons?
Repel.
They don't even do that. What's the charge on a neutron? They're neutral. So electrically, neutrons do not attract or repel. They don't care. How about a proton and a neutron? Do they attract, repel, or they don't care, electrically speaking? Proton's positive, the neutron is not charged, it's neutral. So do they attract, repel, or not care?
Not care.
They not care. The electric charge on the neutron is 0, so they don't care, electrically speaking. The strong nuclear force, by contrast, is an attractive force between nuclear particles, between protons for one another, between neutrons for one another. But it only acts at close range. The two particles have to be nearly on top of one another to feel the strong nuclear force. And so the idea is that you can think of neutrons as being kind of a glue that holds a nucleus together, because the protons in the nucleus repel one another electrically. But the neutrons don't repel one another or the protons electrically, but they do attract them using the strong nuclear force. And so the fact that neutrons don't do anything electrically, but they do participate in the attraction via the strong nuclear force, makes them, you can think of it, roughly speaking, as kind of a glue that's holding the nucleus together. Not literally, but in other words, they're responsible for the fact that the nucleus can be held together, if you will. And that's via the strong nuclear force. The strong nuclear force is what holds nuclei together, despite the electrical repulsion of the protons for one another. Yes?
Did we go over the ideal gas law?
Back in chapter 4, I think we did, or
Okay.
5 or something like that, And it plays a role in the sun in that with the business of it being stable, for example, the solar thermostat. If you increase the temperature of the core, that would raise the pressure because of the ideal gas law. In other words, the ideal gas law says that if you increase the temperature, the pressure rises. And that rise in the pressure is what makes the core expand and cool off again, the solar thermostat. So that's where, at this point, the ideal gas law comes into play. Yes?
Have our questions been close to the test
Ah.
at this point?
I'm not going to tell you that. I'm not going to tell you that because the thing is that, there's an exam has two purposes. One is assessment, right? How well you're doing in the class and all that. The other is to get you to study for it. And so if I told you what's on the exam, you would only study the stuff on the exam, but I want you to study everything is what it comes down to. So, sorry, but I will not reveal that information.
Fair enough.
Other than to say, yes, of course you've asked me to do some things about things. I will say that it's certainly not the case that I'm going to walk out of this and tell my wife, wow, they asked me all these questions and they were good questions, but none of it's on the exam. No, that is not the case. That is not the case. Yes?
There was a math problem on Mastering the Strong, talking about like the annual energy consumption.
Yeah, that's the one he was asking about. That would be one that would be, I don't want people spending the last 15 minutes trying to do that problem, is what it comes down to. Bless you. Yellow Springs, Ohio on there?
It is, yeah.
It is, okay.
Yeah.
I had a former student from Yellow Springs.
Oh, really?
Yeah.
It's a great little town.
Yep. I